Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. So as I've said previously, I will cover the metaforming class in this video lecture. Okay, so this is the final part for metaforming. Okay, so what we are going to see in this lecture will be the last two topic on the bulk deformation. Okay, so today I'm going to cover on extrusion processes and wire and bar drawing. So we go to the extrusion process first. Okay, so what is extrusion? Compression forming process in which work metal is forced to flow through a die opening. Okay, if you remember on the processes that I've already introduced to you, such as rolling is to reduce compression to reduce the thickness. Okay, second we have forging process, compression to form shape, and now we go for the extrusion. It's a compression that force to flow through a die opening. Okay, so this one we force it through die opening to produce a desired cross-sectional shape. Okay, so this one, the shape of the final product will follow the die opening shape. Okay, so this process similar to the squeezing toothpaste. Okay, if you can imagine, if you have a toothpaste and then you squeeze all the toothpaste from that tube. Okay, so that is the basic idea on how extrusion works. Okay, so in general, used to produce long part or uniform cross section. Okay, so meaning that in between of the extrusion process, you are not supposed to you will not be able to change the shape of the product. Okay, so there are two types of basic extrusion, which is direct and indirect extrusion. Okay, so we see the first type of extrusion, which is direct extrusion. The direct extrusion is the schematic diagram is look like this one, where you will push the material, the work material in here, and the work material will come up at the other end of the ramp. Okay, so if the ramp is this side, so the final work will come up on the other side of the die. Okay, so this is the die opening. Okay, so this is the final work shape that you will get. Okay. So here is the video on how it works. Good. If you see here, this is a butt. So this is the butt is a part of material that not able to be pushed through the hole. So this part you have to remove at the end of the process of extrusion. Okay, so direct extrusion also called as forward extrusion because it's going forward. Okay, so starting billet usually is round. Okay, so the cross section of the starting billet is round. Final cross section will follow the die opening shape. Okay, so as ramp approach die opening, a small portion of billet remain that cannot be forced through the die. So this is what I call I mentioned previously is called butt. Okay, by using direct extrusion, you will be able to create a lot of shape, and it can also be hollow or semi-hollow shapes. Okay, so this one is the different come out from this mandrel, meaning on the ramp there'll be another one device or another function that we call mandrel that will create hollow inside the workpiece on the work the final work. Okay, so we can see the video on this one. So if you can see, there's a mandrel inside here that create the hollow inside the extrusion part. Okay, now this is another example. If you can see, this is a mandrel, and then the work part is the thin part. If you can see, this is the final one. Okay, so mandrel will be the support and also the one that give the hollow to the work material. Okay, so another type of extrusion is indirect extrusion. In indirect extrusion, if you can see here, this is the ram that we use, and this is the work part. There is no opening on this side, and the opening is in between the ram. Okay, so if you can see here, it will be a hollow ram. So when you push this part, the work material will come on the same opening, on the same direction, on the opposite direction of the ram. Another method of indirect extrusion is the ram will go in the middle of the work part here. So it will create the hollow inside the work material, and the work material will flow on the side of the ram. So this will create the hollow part of the indirect extrusion. So this one is for the solid one, this one is for the hollow part. Indirect extrusion also is called backward extrusion or reverse extrusion. So if you can see from here, for the direct extrusion, it's going forward, right? So the work material here is going backward. Okay, so that's why it's called backward extrusion or reverse extrusion. So for the limitation for the indirect extrusion, it is lower in rigidity of hollow ram, and it's very difficult to support the extruded part as it exit die. Okay, because it's have this a ram over here, so it's very difficult to support this part. So because of that, we cannot produce a long workpiece on this one. Okay, so the advantage of extrusion is you can produce variety of shapes. So what you have to do is just to design the die opening, but it must be uniform throughout the line. Okay, so another one is grain structure and strength will be enhanced because usually extrusion is done in cold and warm extrusion. Okay, and you will be able to get close tolerance also by using the extrusion process. In some operation, we can see that little or no waste of material will take place. In terms of temperature, the extrusion also can be performed by using hot extrusion and also cold extrusion. Okay, so hot extrusion is usually used for a very intricate parts. If the design of the product is very detailed or very intricate, so it is suggested for you to use the hot extrusion. Okay, so this one, how do we define the hot extrusion and cold extrusion? Is the same like previously I've mentioned. So hot extrusion is 0.5 above 0.5 melting temperature, and cold extrusion is done in the room temperature. As for cold extrusion, usually they will use impact extrusion, which is mean that it will indicate high speed of cold extrusion. Now let's see on the extrusion parameters and analysis. So how do we want to calculate the reduction ratio or extrusion ratio? So here extrusion ratio is indicated as Rx equal to A nodes over A final, A initial over A final. Okay, so A node is the cross-sectional area of the starting billet, and AF is the final cross-sectional area of the extruded section. So this equation applies for both direct and indirect extrusion. So how do we now? We're going to show you the equation for you to find the true strain. Okay, so this one is the condition when there is no friction. So the epsilon equal to ln Rx or equal to ln A naught over AF. Now, how do you want to find the pressure? The pressure is equal to average flow stress times the ln Rx, the through strain. Okay, so then you will get the pressure for on the RAM. Okay, so average flow stress, you use the same equation previously mentioned. So that previously is on the previously the condition is without friction. So now how do we want to calculate the actual through strain? So the actual through strain can be calculated by using this equation. Epsilon x equal to A plus B ln Rx. Okay, so this equation A and B is the empirical constant for a given diangle. So typically A value it will be 0.8 and B is within 1.2 to 1.5. So if you have to calculate the actual through strain, usually you will be given with the value of A and B. Okay, so usually value of A and B will increase with the increasing of diangle. Okay, so we will see what is diangle later. Okay, so the RAM pressure to perform indirect extrusion can be calculated by using this Johnson extrusion strain formula, which is P equal to average flow stress times epsilon x, this one. Okay, compared to the indirect extrusion, friction in the direct extrusion is a little bit complicated. Okay, so this one is depending on the angles and also the length here, where is the length of the touch of workpiece with the die. Okay, so for this one, due to that, the pressure of the RAM calculation is a little bit different from the indirect extrusion. In order to calculate the pressure, this equation is created, so which is PF equal to pi d naught squared over 4. Okay, so this one is the area of cross-sectional area of the billet, pi d naught squared over 4. Okay, so time the PF. Okay, so this one is the additional pressure required to overcome friction, and is equal to this one time. This one is if you remember, this one is the coefficient of friction. Yes, a coefficient of friction at the container wall. Okay, so PC is the pressure of the billet against the container wall, and pi d naught L is the area of the interface between billet and container wall. Okay, so this one usually will be given the value for L and you can calculate it. Okay, so this one, if you arrange, and then you will be able to get the pressure for the direct extrusion. In order to simplify the equation, assumption has been made where the equation has been simplified to this equation. Okay, so now when Ys here is the shear yield strength. Okay, so it assumes that Ys equal to the average flow stress over 2, then the PF can be simplified into this equation. Okay, so now when it is replaced here, you will be able to calculate the P value, which is RAM pressure for the direct extrusion, is given like this one. Okay, so now how do you want to calculate the RAM force? RAM force is calculated by using equation F equal to P times A naught, which is P is the RAM pressure and A naught is the billet area. Finally, we have to calculate the power. Power equal to FV. F is the RAM force and V is the RAM velocity.